Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really interesting headline. Small language models are the future of agentic AI. What are your initial thoughts on this?
Well, I think it's a bold statement, but it aligns with what I've been seeing. The advancements in deep learning, particularly with these smaller, more efficient models, are really impressive. We're packing more intelligence into less space, and that's key for creating truly agentic AI, right? Think about it, an agent needs to be responsive and operate in real time. Big, clunky models just won't cut it.
I'm a bit more skeptical. The small part worries me. Are we just optimizing for size at the expense of actual understanding? It feels like everyone is rushing to scale down models without addressing the fundamental limitations of deep learning itself. I mean, can a smaller language model really reason and understand context in a way that's even remotely close to how a human does?
I agree with Sarah to some extent. My gut feeling is that shrinking the models won't solve the deep-seated issues of how these models represent and manipulate spatial and temporal information. It's like, yeah, you can make a smaller car, but if it still can't navigate a roundabout, what's the point? We need algorithms that can truly understand spatiotemporal relationships, not just brute force statistical correlations.
That's a great point, Donald. And Sarah, I share your concern about the understanding piece. I think we need to be careful about equating clever language generation with a genuine agency. I mean, a parrot can mimic speech, but it doesn't understand what it's saying, right? So what does it actually mean for these small language models to be agentic?
But aren't we seeing evidence that these models are going beyond simple mimicry? Think about the ability to fine-tune these models on specific tasks. The article highlights the fact that fine-tuning them enhances the model's capacity to represent and manipulate concepts. It's like giving the model a focused education that allows it to reason and act in a more targeted way. It's not just regurgitating data, it's learning to apply it.
Okay, but fine-tuning is still just tweaking the connections in a vast network. It doesn't address the fundamental need for symbolic representation and reasoning. A neurosymbolic approach, where we combine the strengths of neural networks with symbolic AI, might be a better path. Imagine a system that can not only recognize patterns, but also reason logically about them.
Yeah, that resonates with me. It's about representation, not just correlation. Can these language models translate between different coordinate representations? If I describe a scene using Cartesian coordinates and then switch to polar coordinates, can the model understand that it's still the same scene? That's the kind of spatiotemporal reasoning that I think is crucial for true agency, that I'm not sure deep learning alone can get us there.
Right, it's about grounding the model in the real world. Neuroscience emphasizes the importance of embodiment and the environment in shaping cognition. These language models, even the small ones, seem to exist in this abstract, disembodied space. How can we bridge that gap? How can we incorporate the principles of embodied cognition into the architecture?
Well, think about the advancements in robotics. We're seeing these language models integrated into physical robots, allowing them to interact with the environment and learn from experience. That interaction with the real world is the embodiment you're talking about. The robot learns by doing, by seeing, by touching, and the language model helps it to interpret those experiences and plan actions.
But is it really learning in the way a human does? Or is it just learning to predict the next best action based on a massive data set of previous actions? There's a difference between mimicking intelligence and actually possessing it. I'm afraid we're focusing too much on the former and not enough on the latter.
Exactly. And it comes back to the algorithm's ability to understand the underlying physics of the world. Can it predict how objects will interact with each other based on their shape, mass, and velocity? Can it plan a sequence of actions that takes into account these physical constraints? That requires a deeper understanding of spatiotemporal relationships than I think these language models currently possess.
So let's dig a little deeper into this concept of where fine-tuning that the article mentioned. It suggests that fine-tuning can enhance the model's capacity to represent and manipulate concepts. How does that actually work? And is it truly moving us closer to genuine understanding?
Well, from my perspective, it's about creating a hierarchy of abstraction. You're essentially teaching the model to recognize and understand fundamental concepts at deeper layers. This allows it to make more informed decisions and generalize to new situations. It's like giving the model a set of building blocks that it can use to construct more complex representations.
But how are these concepts represented within the model? Are they just another set of weights and biases? If so, then I'm skeptical that it's truly leading to understanding. We need a more explicit way to represent knowledge, a way that allows the model to reason logically and make inferences. That's where symbolic AI comes in.
And how does the model relate these concepts to the real world? Can it understand that the concept of apple is related to a physical object that exists in a specific location in space and time? Can it understand that the apple can be moved, eaten, and transformed? That requires a spatiotemporal understanding that goes beyond simply recognizing the word apple.
That's a key point. If we can map learned concepts to neural circuit activity patterns potentially observed in brain imaging, then we have a more tangible link between the model's internal representations and human cognition. This opens doors for cross-validation and an understanding of how the model's reasoning might translate into neurobiological functions.
Yeah, I agree that understanding the internal workings of these models is crucial. But even if we don't fully understand them, the fact that they're able to perform complex tasks suggests that they're capturing something important about intelligence. We shouldn't dismiss the power of data-driven intelligence just because we don't fully understand how it works.
But blindly trusting these black boxes is dangerous. We need to be able to explain their decisions, to understand their biases, and to ensure that they're not making harmful predictions. That requires a more transparent and interpretable approach to AI, which is why I'm so passionate about neurosymbolic methods.
And it requires an algorithm that can adapt to different coordinate systems. If the model is trained to recognize objects in a specific orientation, will it still be able to recognize them when they're rotated or viewed from a different angle? That kind of invariance requires a deeper understanding of spatial transformations.
So let's bring it back to the headline. Small language models are the future of agentic AI. What are the key challenges we need to overcome to make that a reality?
I think the biggest challenge is scalability. Can we continue to shrink these models without sacrificing performance? And can we develop more efficient training methods that allow us to train them on even larger datasets? The sheer volume of data is what's driving the progress, so we need to figure out how to leverage that more effectively. Think about data augmentation techniques to create more diverse and representative training datasets. That's going to be critical.
I think the key challenge is moving beyond pattern recognition to true understanding. We need to develop algorithms that can reason logically, make inferences, and understand context. That requires a more principled approach to representing knowledge, not just tweaking connections in a vast network.
I think the biggest challenge is developing algorithms that can truly understand spatiotemporal relationships. We need to move beyond treating time as a separate, one-dimensional sequence and integrate it intrinsically with space. And we need to develop algorithms that can seamlessly translate between different coordinate representations.
I agree with all of you. I think we need to take a more biologically inspired approach to AI. We need to understand how the brain actually creates agency, how it integrates perception, action, and cognition. And we need to translate those principles into computational models.
It's also about exploring the potential of transfer learning. If we can train a model on one task and then transfer that knowledge to a completely different task, that would be a huge step forward. It would allow us to build more versatile and adaptable AI systems.
Yes, and that's where neurosymbolic AI could really shine. Imagine a system that can learn a set of symbolic rules from one task and then apply those rules to a completely different task. That would be a much more efficient and robust approach than simply retraining a deep learning model from scratch.
The algorithm also needs to be able to handle uncertainty. The real world is messy and unpredictable. The model needs to be able to reason about probabilities and make decisions even when the information is incomplete or noisy. And it needs to be able to learn from its mistakes and adapt to changing circumstances.
And it needs to be able to do all of this in a way that's ethical and responsible. We need to be mindful of the potential risks of AI and ensure that it's used for good, not for harm.
Okay, so if we're talking about future research directions, from my perspective, it's all about scaling up these small language models. We need to figure out how to train them on even larger datasets, how to optimize their architecture, and how to make them more efficient. The key is finding the optimal balance between size, performance, and computational cost.
I think the future research direction is in developing more robust neurosymbolic algorithms. We need to find ways to combine the strengths of neural networks with symbolic AI to create systems that can both recognize patterns and reason logically. And we need to develop better ways to represent knowledge in a way that can be easily reasoned with.
I think the future research direction is in developing algorithms that can truly understand spatiotemporal relationships. We need to move beyond treating time as a separate dimension and integrate it intrinsically with space. And we need to develop algorithms that can seamlessly translate between different coordinate representations. It also has to have a coordinate system that is flexible enough to support translation.
And from my perspective, the future research direction is in taking a more biologically inspired approach to AI. We need to understand how the brain actually creates agency, how it integrates perception, action, and cognition. We can incorporate neurobiological principles of concept formation and categorization into the training process.
One concrete example of research that aligns with my thinking is exploring the use of generative adversarial networks GANs to create synthetic training data. This could help us to overcome the limitations of real-world datasets and train models that are more robust and generalizable. Imagine GANs generating endless variations of scenarios, each subtly different, forcing the model to truly understand the underlying concepts.
For me, it's about developing a formal language for representing knowledge that can be easily manipulated by both neural networks and symbolic reasoning engines. Think about a system that can learn to represent knowledge in a structured way, like a knowledge graph, and then use that knowledge to answer questions, make predictions, and plan actions.
My focus would be on developing a neural architecture that natively supports multiple coordinate representations. I'm thinking about something like a hierarchical network where each layer represents a different coordinate system, and the connections between layers allow for seamless translation between them. Imagine a model that can effortlessly switch between Cartesian, polar, and cylindrical coordinates, depending on the task at hand.
I'm interested in exploring the use of recurrent neural networks to model the dynamic interplay between different brain regions. Think about a model that can capture the feedback loops between the prefrontal cortex, the hippocampus, and the amygdala, and how those loops contribute to decision-making and goal-directed behavior. That would require a deep understanding of the temporal dynamics of neural activity.
Yeah, and tying that back to the original article, think about the implications for things like customer service bots. Imagine a customer service bot that can not only understand your questions, but also empathize with your emotions and provide personalized solutions. That's the kind of agentic AI that these small language models could enable.
But only if we can ensure that those bots are fair, unbiased, and transparent. We need to be able to understand how they're making decisions and to correct any biases that might be present in the training data. Otherwise, we risk creating AI systems that perpetuate existing inequalities.
And only if they can understand the context of the conversation. Can the bot understand that you're frustrated because you've been on hold for an hour? Can it understand that you're asking for a refund because the product you received was damaged? That requires a deeper understanding of the situation than I think these language models currently possess.
Absolutely. It also needs to understand the underlying intent behind the question. Are you simply looking for information, or are you trying to solve a problem? The model needs to be able to infer your goals and provide assistance accordingly.
So it sounds like we all agree that while small language models show promise, they're not a silver bullet. There's still a lot of work to be done to create truly agentic AI. But it's an exciting field, and I'm optimistic about the future.
I agree. It's a fascinating area of research, and I'm excited to see what the future holds. But we need to be careful not to get caught up in the hype and to focus on building AI systems that are truly intelligent, ethical, and beneficial to society.
Agreed. The key is to move beyond brute force pattern recognition and to develop algorithms that can truly understand the world around them. And that requires a more holistic approach that integrates insights from neuroscience, cognitive science, and computer science.
Well, that's all the time we have for today. Thank you all for joining me for this fascinating discussion. And thank you to our listeners for tuning into Cognitive Spirals. We'll be back next week with another exciting topic.
Thanks for having me. It was a great conversation.
Thank you. Always a pleasure.
My pleasure as well. Looking forward to the next one.